Hi, this is Dr. Staley. Today we're going to be doing the Chemical Reactions Lab Part 1 for Introductory Chemistry. We've got 4 different things to get through today. First, we're going to be burning a strip of magnesium, and we're going to be testing the ashes from it to see if it's more acidic or basic. Second, we're going to be reacting a strip of magnesium with some hydrochloric acid in order to see how the reaction goes there, and we're going to compare that to reacting calcium carbonate, or the main component of chalk, with hydrochloric acid. Thirdly, we're going to be looking at 3 different solutions, and we're going to see how acidic they are compared to one another by reacting them with sodium hydroxide in the presence of an indicator. And fourthly, we're going to be looking at some precipitation reactions, where things that are dissolved in solution come together and form a new product. Now, to start with, let us look at the setup. So, I'm keeping most of my materials on a couple of paper towels. This serves the purpose of making sure that if something falls down, there's at least a tiny bit of a cushion, and also if something gets wet and I put it down, it doesn't leach onto something else. And lastly, it makes it really easy to clean up afterwards. But that's not the whole thing that I'm doing. I've also got this part here with my Bunsen burner, which I'm going to use to actually light the magnesium, my watch glass, which I'm going to use to collect the ashes, and of course my notebook with pen that I'm going to use to record my observations. Now, important to remember about all of this is that I don't want to burn the magnesium too terribly close to anything flammable. So I've got to put this stuff over here to the side of it and keep the Bunsen burner way over here. So, the first step of burning the magnesium, you've got, of course, the magnesium strips. And the first step that we have to do before we do anything else is we need to make sure that the magnesium strips are going to burn as much as possible and as quickly as possible. Now, you might not be able to see it that well, but this piece of magnesium is kind of dull. It's not very shiny. The reason for that is that all metals except for gold and platinum react with oxygen in the air, and so that causes them to develop a layer of metal oxide on their surface. So this right here is magnesium with magnesium oxide on the surface. That magnesium oxide is a barrier to any and all chemical reactions, such as, burning. So what we're going to do is we're going to use a piece of sandpaper. We're just going to sand this sucker down. So that we remove that top magnesium oxide layer. And that layer will start reforming as soon as it is removed, but it's not going to be done reforming before we start to actually light it on fire. That's pretty decent for that side. Let's do the other end. Here. There we go. So this is now a lot shinier than it used to be because I've scrubbed it nice and clean. Now, next thing is a Bunsen burner. Let me show you something here. So, there are 3 different nozzles here. At some of the hoods, those things, at some of those hoods, there are even more nozzles. And it's important to look at the labels. This one is labeled VAC, for vacuum. This one is labeled AIR for air. And this one is the gas nozzle. But it's also blue. Now, I've had 2 different instances where students have needed to use a nozzle like this that cold water came out of. The problem is that those nozzles are labeled green, and they're labeled CW for cold water. But they accidentally hooked their stuff up to the blue one instead, because they thought, oh, blue, well, that's the color of the ocean. Now, you need to read the label. The blue ones here, they're the gas. So I take my Bunsen burner, I put it onto the gas, I make sure that this isn't getting very much air, so that I have a good, strong, large amount of natural gas coming out. When you're first starting it up, that's what you do. Just like with a gas-powered motor. You got the choke chain. What does the choke... You got the choke on. What does the choke do? It restricts the airflow into the engine. Alright, so here we go. Step 1, light the match. Step 2, put the match next to the outlet. Step 3, curse the match because it went out while you were describing things to people. You always want the match next to the outlet, because if it's not, then when the natural gas starts to come out, it'll blow out the match instead of lighting. You always want to have the match next to the outlet before you turn on the natural gas, because if you don't, then you'll get a bunch of natural gas right in your face, and when you do finally light it, you'll end up with a minor explosion instead of the flame. This is our flame, but it's not good enough. You see how it's pretty much all yellow? Well, I'm colorblind, so to me it's yellow. There could be some reds in there. So the way we get it so that more of it is blue, because that's what we want it to burn hotter, and when it burns hotter it's going to turn blue. We're going to open up this valve right here to let more oxygen in. And if you notice, there's blue at the bottom here where it's the hottest. And as I open it up and let more oxygen in, more and more is going to turn blue. Keep going, keep going, keep going. There we are. So that's about as good as I'm going to get. So if I restrict some of the gas flow, will the mixture be better? Yeah, there we are. Okay, so this is good enough for our purposes. Now, you see, there are basically 2 cones of flame, because the gas is coming out here and it's reacting right at this rim. So on the outer cone is farther out and is closer to room temperature air. So it actually is going to cool down the fastest. The inner cone comes to a point right about here. That's the part, that is the hottest part of the flame. Now, if I, messed around with this, I could get it even. I could get it even better, and that inner cone would be down about here. If I did that, then it would be hot enough to melt glass. We don't need it quite that hot for our experiment. It'd be nice if I could get it that hot. Come on, you. Oh well. We don't need it quite that hot for our experiment, so let's just not do that, and let's call it good enough instead. This is the magnesium. I'm holding it with crucible tongs. You do not want to hold this with your finger, and also you do not want to have it burning while on a piece of glass. Hold it by the barest minimum that I think I can get away with. And let's go ahead and put it in this flame. Okay, cool. That was a bright flame. Now it did not completely burn. I've still got a tiny piece of magnesium right here. So let me see if I can get a little bit more to burn. The answer is probably no, because that white stuff on it is a mixture of magnesium oxide and magnesium nitride. So that's probably going to be a pretty decent barrier against it catching on fire again right away. Yeah, no. Okay. Do that, and let's put this off to the side here, so I can deal with it later. So now that I'm finished burning the magnesium, I can turn off the flame. And there are lots of different definitions for an acid or a base. But we're going to go with the Arrhenius definition, which is when you add it to water, what does it do to the H plus concentration? So we have our ash, and we're going to add some deionized water to it. Go out here, let's rinse off the tongs, get that in there. Now, magnesium oxide is not terribly soluble in water. So basically what is going to react here is the surface of the magnesium oxide particles. It's pretty much going to stay a solid while it's in there. But if we crush the particles a little bit and stir them around a little bit, then we can expose more surface area. And so we can get it to interact with the water a lot more. Okay, that's good enough. So next up, we're going to test it with some pH paper. And the way you do that is you take out the pH paper, you take a whole strip and you dip the whole thing in. No, I'm joking, obviously. No, so pH paper is not horrifyingly expensive, but there's still no point in really wasting the pH paper. So what we do instead is we take it and we tear off a small piece and we place that small piece onto another watch glass, like that. And then we use a glass stirring rod to dab, 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 and add some liquid to the pH paper. Now, before I actually do that, I need to talk about this a little bit. So, this is red pH. This is red litmus paper. Excuse me, it's not pH paper, it's litmus paper. So this right here is red litmus paper. It has a dye in it that undergoes acid-base reactions. When that dye has reacted with an acid, it is red. When it has reacted with a base, it's blue. So, I'm just going to put that down right there. This is red. Now, if this solution is acidic, then when I use it on there, it'll stay red. If this solution is neutral, then when I use the solution on there, it'll also stay red. The only way it changes is if the solution is blue. The only way it changes to blue is if the solution is net basic. So we take our stir rod, and we get some of the liquid on, and we add it to our pH paper. Just adding a little bit more. So it has changed from red to kind of, I don't know, what do you call that? Pinkish, purplish. Yeah, see, one of the problems is that the video that I'm seeing is lower quality than the video that it's going to end up being. So I can't so I don't actually know if you can see that. But it's actually kind of bluish there. Now, let's try it again just to be sure. Yeah, so I've kind of got the same thing again, where it looks like it's turning maybe a little bit pinkish, maybe a little bit purplish, but it's kind of hard to see. It's kind of hard to say. So let's go ahead and let's use the blue pH paper, the blue litmus paper. Once again, we remove one strip, we tear off a little piece, and because I use two pieces of the red for two different tests, I'll use two pieces of the blue for two different tests. There we go. Now, the blue pH paper, the blue litmus paper contains the same dye that the red litmus paper does. The only difference is that prior to being packaged, the red litmus paper was reacted with an acid to make sure it started out in the red state, and the blue litmus paper was reacted with the base in order to make sure that it started out in the blue state. So here, if this is acidic, then the blue litmus paper will change to red, and if it is basic, then it will stay blue, and if it is neutral, then it will also stay blue. And so there is the results. These two right here are the blue litmus paper pieces that I just tested. Now they are very, very, very definitely blue. And if you look over here at the red litmus paper, pieces of it are red, but pieces of it are blue also. So I would say that probably means that this is basic, but very weakly basic, as opposed to being acidic or neutral. So, now before we go on, write down our notes. Now, the first thing that I noticed when I went to burn the magnesium was that it took a little while to ignite. The second thing I noticed was that when it ignited, it basically did it in two different phases. So when it ignited, it started glowing yellow and deforming. Then it turned a blinding white. So first, it got really, really hot. It turned yellow, and the edge of it kind of started to fold in like that, like it was almost melting. And then after it did that, boom, that's when the really, really bright white light started. Okay, now there was a lot of smoke. I think the smoke looked pretty dark colored, and there was a white powder left over. Now, finally, the observations from the litmus paper. I'm not going to write down that the solution that I made by mixing the powder with DI water, I'm not going to write down that that was basic. I'm not going to write that down here, because that's not an observation. That is a conclusion. That's an analysis. That's an explanation. The observations are that when the mixture was tested with red litmus paper, parts of the paper turned blue, and when the mixture was tested with blue litmus paper, it stayed blue. Okay, so that's it for the burning of the magnesium. The next step is reacting first the magnesium and then calcium carbonate with hydrochloric acid. So, now is the part where we're going to react first some magnesium metal, then some calcium carbonate with hydrochloric acid. I have my test tube labeled magnesium on top, HCl on the bottom. There's the little piece of magnesium, nice and polished. And similarly, I have my calcium carbonate. Ca is calcium, CO3 is carbonate, and HCl. Calcium carbonate is already in there. It's a white powder. And I'm going to add some 1 molar hydrochloric acid. Now, the instructions say to add about a milliliter, and I'm going to let you in on a little secret. At room temperature, at atmospheric pressure, the surface tension of water is such that 1 milliliter is about 20 drops. So if you have one of these, and you don't need to be super exact, you can just count out 20 drops, and that's 1 milliliter. So here we go. That's 20. Ooh, check it out. I actually want to do a quick little experiment here. Let's light a match. Did you hear that? There was a little pop, and the flame got a little bit bigger when I put it over the mouth. That is pretty interesting to me. Now also, on the bottom here, it's getting really, really hot. So that is also interesting to me. So, that's going. We do have our calcium carbonate still. So once again, let's do 20 drops. There, so you can see it. Okay. So it started fizzing basically immediately upon adding the drops. I'm holding the bottom here with my fingers. It's a little cold, actually. Yeah, the bottom definitely feels cooler than the glass on top of it. Now let's try the thing with the... this time. That's interesting. So not only is there not a pop here, there very definitely is not a pop, but when I put the lit match over the mouth of the test tube, the flame went down a bit. And quite naturally, we're going to do this a second time. Here we go. Once again, it's fizzing. Ooh, that's a lot of fizz. So once again, let's try this with the match. And put it here. Yep, flame's definitely going down. It's okay. Definitely goes down. So whatever is coming out of here is making it hard for the flame to survive. Whereas what was coming out of here was making it easy for the flame to survive. And so, naturally, we have to write down our observations. So, we're going to take these in two columns. The left column I'm going to put for the magnesium and the 1 molar hydrochloric acid. The right column is going to be for the calcium carbonate and the 1 molar hydrochloric acid. So in both cases, a reaction started right away where they started fizzing and it produced a lot of bubbles. There was some kind of reaction that caused bubbles. Now, bubbles aren't just nothing. What they are is they're gas. So that means that it's released a gas. The solution did not change color and it did not get cloudy. So here's the first magnesium and calcium carbonate that I did. And you can see that the solution is still clear and it's still colorless. However, there are a couple of differences. So for the magnesium, the water in the bottom, where the solution was, got hot. Whereas with the calcium carbonate, the water in the bottom got, I don't want to say cold, how about colder than it was. The other thing was the matches. So over the magnesium, the match had no trouble staying lit and made a pop. Whereas over the calcium carbonate, the match did have trouble staying lit. And it smoked a lot more. Okay, so that's it for part one. Okay, so next up, what we're going to be doing is we're going to be looking at a couple different substances dissolved in water to see if they're more acidic or basic. Now, just like before, we need our blue litmus papers and our red litmus papers, because if the blue paper turns red, then it's probably acidic. If the blue paper stays blue, it's either basic or it's neutral. Similarly, if the red litmus paper stays red, it's either acidic or neutral, and if it turns blue, well, then it's basic. Now, on our list, so first off, got my tables all set up. Now on the list, first we have 0.1 molar HCl. Let's start out with the blue litmus paper. And I'll do this one here. There we go. Let's do this one here on the end. Just need one drop. Oh, look at that. Turns really, really, really red. And it looks like it is, like that drop is starting to spread. Let's get the other litmus paper out of the way, and let's soak up the rest of that drop before it interferes with any other litmus papers. Stupid things. Before it interferes with any other litmus papers, and thus interferes with our experiments. There we go. Now, just doing the blue litmus paper isn't always enough. Let's look at the red litmus paper. And it looks like it is staying red. So now let's go ahead and soak up the extra HCl solution so it doesn't dribble its way onto any of the other papers. Next up, the KOH. Now you might notice that I'm covering the actual names of these. That's because the chemicals have to be properly labeled with their names. And some of the names end in acid, which would kind of give away which ones are acids and which ones are not. So, for the KOH, that's us. Do this right here. Now, you might notice that I have a red litmus paper right there. I do that on purpose because the watch glass that I got for this one isn't nearly big enough, and it's just more convenient if I put one of the red pieces over here. Alright, so start with the blue. One drop. What does it do? What does it do? Looks to me like a whole lot of nothing. Alright, so now let's go with the red piece that's right here. Come on. You can go off of there. Oh, just go. Oh! That one turned blue instantly. Instantly. Cool. So now let's go ahead and suck this up. By the by, before I do anything else, there's something important that I want to point out to you. And that, oh, wait. No, not yet. Later. In a little bit. So, next on our list is the is the NaOH. So here we go. Now let us once again start with the blue litmus paper. There we go. Soaking into the blue paper, and a whole lot of nothing. No change. Stupid thing. Soak up the stuff on the edges. Let's go back to the red. And instantly turns blue. Cool. So next, we're going to use the DI water. We're going to start with the blue litmus paper. Just do a little bit of that. Oh, so it's staying blue. Soak this up so that we don't. Now with the red litmus paper, what we have here, it is staying red. So next up is the 0.1 molar H2SO4. This one. Now let's take a look at this with the blue litmus paper. Oh, turns red right away. Okay. And with the red litmus paper, that is definitely staying red. Most definitely. Then lastly, the CH3 COOH, or on the worksheet it's listed as HC2H3O2. Let's test it on the blue litmus paper. Nope. Nope. Come on. It's one of the great things about wearing gloves. You can actually just move these around without affecting it with stuff on your for your skin. Alright, so that's that one that I just used, and it has definitely turned from blue to red. Cool. Now lastly, this one right here. And that is definitely staying red. Definitely, absolutely 100%. Okay, awesome. So those are the observations about the ones that are acidic and basic. So, let's review. For the HCl, the blue litmus paper turned red. The red litmus paper stayed red. For KOH, the blue litmus paper stayed blue. The red litmus paper turned blue. For NaOH, the blue litmus paper stayed blue. The red litmus paper turned blue. For water, the blue litmus paper stayed blue. The red litmus paper stayed red. For H2SO4, the blue litmus paper turned red. The red litmus paper stayed red. And for HC2H3O2, the blue litmus paper turned red, and the red litmus paper stayed red. Okay, so now what we're going to do is we're going to see so based upon this information, we can figure out which of these chemicals are acids and which ones are bases. And so according to then in our next step, we're going to see how strong these acids and bases, are relative to each other. So here, spoiler alert for part number 2, but the two strongest acids that we used before were hydrochloric acid, HCl, and H2SO4, sulfuric acid. What we're going to do here is we're going to take these 3 samples of sodium hydroxide and we're going to react them with hydrochloric acid, and then we're going to take these 3 samples of sodium hydroxide, which is one of the strongest bases, and we're going to react them with sulfuric acid. Now here I've labeled them NaOH, that's the base that we're using, and H2SO4, and then a number. So this is trial number 1, trial number 2, and trial number 3. And what we're going to do is we're going to see which of these acids is the strongest. And we're going to see that by seeing which of these acids reacts the most completely. Which one takes less acid to react completely with the sodium hydroxide. But how do we tell it's reacted, you ask? Well, we have an indicator, a dye that reacts with acids and bases and is one color when it's around acids, and a different color when it's around bases. So when the acid and base react, whichever one is left over is going to determine the color of the dye. The dye we're going to use today is phenolphthalein. So let's add some here to our sodium hydroxide, the one we're going to react with hydrochloric acid once. Boom. See that nice, I don't know, to me it looks bluish or so. Or, no, purplish. I'm sorry about that. Purplish. And I'm going to add another drop, just to be sure that the color is nice and dark and therefore easy to see. And if you notice with phenolphthalein, it starts out in the bottle uncolored. So in the presence of base, it turns that purplish color. And in the presence of acid, it has no color. I'm going to go ahead and do that to the rest of the test tubes. To each of these test tubes, I've added 10 drops of what is supposed to be 0.1 molar sodium hydroxide. Before I start, I need to caution you. I say supposed to be for a reason. It's because there is carbon dioxide in the air, and when that carbon dioxide dissolves in the water, it becomes carbonic acid. And that can react with strong bases, and when some of the sodium hydroxide has reacted with the carbonic acid, there isn't as much sodium hydroxide left. So it's important to keep your bases sealed when you are not using them, and then only bring them out and only prepare the test tubes right before you're about to use it. So let's start off here with our hydrochloric acid. What I'm going to do is while I add the hydrochloric acid, I'm going to just be flicking this very gently so that it mixes without, spilling out onto me. Drop number 1. Nothing. Drop number 2. Still apparently no change. Drop number 3. No change. Drop number 4. Same, so let me get it so that my white lab coat is in the background. 5, 6, 7, 8, 9. No change still? Seriously? Oh, well, it's maybe a little bit lighter. Maybe a little bit lighter. Ten. 11. 12. 13. One of the drops went on the lip there without actually going in. So let me just get that. I don't have provisions here for 1/3 of a drop or 1/12 of a drop or something like that. Actually, this will be easier. No. I'll just keep doing it like this. $12, $13. $14. $15. $16, $17. $18, $19, $20. $21. $22. Oh, that looks like it's maybe a little bit lighter. 23. $24. $25. $26. $27. $28. $29. $30. $31. I can definitely see it getting clear in there. 33. Yeah, wherever the drop lands. 34. 35. $36, $37, $38. Oops. Went all the way down to 38 there. That was a mistake. But looks like the color is just about gone here. Yep, the color is all the way gone. Okay, so it took going all the way up to 38. However, I overshot it. So it's somewhere between 35 and 38. Now, I have so number 2, There we go. Since I know that the first one took somewhere between 35 and 38 drops, what that means is that I can basically put in 30 really quickly and just get really, really close right away. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Making sure it's mixed. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Darn, I keep forgetting how high that camera is. No, it needs to be like that so you can see it against the white of my lab coat. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Ooh. Yeah, there it definitely changed from purplish to bluish. Or maybe that's pinkish. One. 32. 33. 34. 35. 36. 37. 38. 39. 40. Oh, there we go. 39 didn't quite do it. It happened at 40. Yep, there's still a few wisps of the colored dye in there, but mostly it's clear. So we've got 38 and we've got 40. Let's write those down. And number 3. Run number 3 with the hydrochloric acid. So again, I'm just going to get to 30 really quickly. 1, 2, 3, 4, 5, 6, 7, Okay. Now, here. 31, 32. 33. 34. 35. 36. 37, 38. Ooh. There we go. A couple wisps of color, but it's pretty much gone otherwise. 38. So next up, the sulfuric acid. Put the hydrochloric out of the way. And let's do it with the sulfuric acid. Here we go. One, two, three, 4, 5, 6, 7, 8. Oh wow. At 8 it is already completely clear. Now let's do it with this one. Run number 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. At 9 it changed completely. And lastly, run number 3 with the NaOH and sulfuric acid. One, 2, 3, 4, 5, 6. The first one changed at 8, the second one changed at 9. So I figure out that I'm safe going all the way up to 6 quickly. 7. 8. 9. Completely clear now. Nine drops. So which of these acids do you think is stronger? The hydrochloric acid or the sulfuric acid? Now, when we have a homogeneous mixture, it can become a heterogeneous mixture if something comes out. So right now, this right here is a solution of sodium sulfate, and sodium sulfate dissolves in water. So this is sodium sulfate in water. The thing is, though, that whether or not a given substance will dissolve in water or in some other liquid depends on how strongly the components of that substance interact with the solvent, in this case the water, versus how strongly they interact with each other. So if they interact with each other very, very strongly, then they can grab onto one another and they can form a solid. If they don't so much, well then the water can go in and form pairs with them and stick to them and carry the pieces away from one another. So in the case of sodium sulfate, the sodium ions and the sulfate ions get carried away from each other by the water. However, if we were to add in something like barium chloride, so barium chloride, here's a solution of it right here, also in water. Sodium and sulfate don't stick to each other enough to be solids in water. Barium and chloride don't stick to each other enough to be solids in water. But if we add the two, then they trade partners. Then they trade partners. You see how this is very milky, how it's very cloudy? That's because one of the ions that was in the sodium sulfate and one of the ions that was in the barium chloride have grabbed each other and are interacting so strongly that they form a solid. And because those solid particles start out really, really small, they diffract light going through the water very effectively. Now here, I have a solution of barium chloride. I'm going to add to it sodium sulfate because, you know, it's worth doing the experiment twice. And also, I don't know, maybe there's some sleight of hand. Maybe if I add the sodium sulfate to the barium chloride instead of the other way around, something different will happen. Nope, same thing. Now, in the worksheet that's part of this experiment, I want you to take a look at the solubility rules. The solubility rules were discovered basically through just trial and error, seeing what dissolves and what doesn't. And I want you to figure out, in both of these cases, we know that when barium is paired with chloride, it dissolves in water. We know that when sodium is paired with sulfate, it dissolves in water. So which of these ions came together to form the milky white precipitates? And which of these ions did not and are still dissolved in the water that's around the milky white precipitate and flowing through the milky white precipitate? There is one additional set of questions after that, with a set of reactions that I want you to predict the precipitate and the spectator ions for, and that concludes our experiment. Thank you.